So one of the questions students usually have is, why would I want to use a system of equations? Like, why would I want to have to solve more than one equation at a time? And the reason for this is for the usefulness. So you suppose you have a problem with multiple constraints. I believe we've done what I always call the garden problem. And those are the problems where you have a certain amount of fencing, and say 50 feet of fence, but also you want the garden to be twice as long as it is wide. So you have a constraint that tells you, one, how much fence total, and two, it tells you kind of what the shape of the garden needs to be. It has to be twice as long as wide. Now it could be 10 feet long and 5 feet wide, or it could be 20 feet long and 10 feet wide. The problem doesn't specifically tell you that, it just tells you what the relationship between length and width has to be, and then also that 50 feet of fencing tells you how much total fence you're going to end up using. Sometimes it's easier to think of a problem with multiple equations instead of one. So an example of that might be you have a puddle that's growing, so something's leaking. Some water barrel has a hole in it and it's leaking out water, and this puddle is growing. So the puddle grows, it's a circle, and it grows in area, pi r squared, that's our formula for area of a circle. But also there's an equation that tells you something about how fast the water flows out. So it's harder to think of one equation to describe both of those, but it's pretty easy to think of two separate equations for each. In a timely example, you could have something that tells you about, how fast a virus spreads, likelihood of getting infected, how long it takes to be recovered. That's what we call actually an SIR model. It's very common. These are well studied. But that's actually a system of equations, and each one of those equations gives you a different set of parameters that help describe your system. So the reasons we would want to use systems are, you have a problem with multiple constraints like total fence, dimension, relationships, or the SIR model, so spreading rate, recovery rate, infection rate, or it's easier to think of the problem using multiple, like puddle is growing. All right, so we're gonna start with R1, and you guys will have to just be a little bit patient while I learn how to write on this, but hopefully it works not too bad. 8R1, which is systems, oops, I'm going to abbreviate it as system of equations graphing. So we actually haven't talked about what a system of equations is yet, and the first question students usually have is, why would I want to do a system of equations? So a system of equations So a system of equations is two or more equations which must be solved simultaneously. So what I mean by that is, it's not enough for just one of them to be true. but you know, both or all of them need to be true at the same time. And remember, I drew that triangle at the beginning of this when we started doing lines. That triangle was solution to an equation, makes the equation true, lies on the graph. So if you need to solve them simultaneously, then you need a point that makes both of them true, or a point that is a solution to both of them, or equivalently, a point that is on both graphs. So we're going to come back to that in a second. First, let's look at what some systems look like. So you guys presumably have already done those guided notes. You've kind of seen them. I want to write, I don't know, just maybe one up that we're going to come back and solve in a second. So 3x minus 2y oh, no, it's on. Equals 0, and x minus 2y equals 4. So usually we write one on each line, and then we don't want them to get lost, so we connect them with this little curly brace. Just on one side, though, not on both sides. So this is a system, and usually I find that it's useful to number them. So I would number them as equation 1 and equation 2, because later I'm going to want to talk about them. Okay, so like I said, if you are a solution to an equation, then you make the equation true and you lay on the graph. So since a solution to a system has to lie on the graph of both of the equations, that means that it's going to be where the lines intersect. So since since solutions to systems must solve both equations, they will lie on both graphs, i.e., solutions will be where graphs intersect. Okay. So in the guided notes that you look through, they do 2 examples of show the point is or is not a solution. That's just plugging in if it's true for both, yes. If it's true only for one of them, then no. You can have a system with more than more than 2 equations. You can have however many you want. In this class, we're just going to focus on